Okay, everyone, thank you for waiting. So we'll start on our webinar about an online virtual tool to simulate microalgae cultivation in Raceway Reactors. This webinar will start by a small introduction by Professor Gabriel Assien, followed by the presentation of 3 projects, DigitAlgesation, ALGAENAUTS and Realm, and followed by the simulator presented by José Luis Guzmán. If you have any questions, feel free to use the Q&A, and you will all be muted to prevent any disruption to the webinar. The webinar will be recorded and made available afterwards using the same email you used to register. So feel free to rewatch it later and save your questions to the end. And now we'll start with Professor Gabriel.
Hello, Mariana.
Hi.
I will start to share my screen. Sorry. Must do. A moment. Can you see my screen?
Not yet.
Now?
Not yet.
Sorry. 1 second. Pantalla.
Yes, now you're sharing the desk. Yes, the
Okay.
presentation.
I think now it's in full mode.
Yes, perfect.
Okay, thank you. Thank you, and thanks to all
sorry,
the
Sorry,
yes?
Gabriel, can you minimize the window? That window, yeah, perfect.
Okay.
Go ahead.
Thank you to all the participants in this webinar. I will introduce very briefly the major factors to be considered about the large-scale production of microalgae system as basis for the later discussion with José Luis about the simulation tools, etc., as part of the real project. Then, as probably all of the attenders already know, the actual production facilities are more or less based in 2 major technologies, Raceway Reactors and tubular system. All of them are working for different purposes, production of microalgae biomass for different applications around the world. And they are reliable technologies. The challenge is to be able to scale up these production facilities, and of course, always to optimize the production in terms of higher productivity and lower production costs. Then the overall characteristic of all these facilities or technologies is that we must face with 3 major aspects. The first one is the biological system. We must recognize that today we are using only few strains. Most of them are only extremophile strains, very, very high salinity or alkaline conditions. Including we are managing these strains more or less in a static way. I mean, considering the optimal culture conditions that we determine in the laboratory, then to try to mimic these conditions in the outdoor reactors. Concerning the engineering of the reactors, we are using this type of conventional technologies, Raceway Reactor and tubular system, but the current scale is not yet sufficient for huge application of microalgae biomass, and including due to the complexity of control system, we are not controlling adequately the culture conditions already in the culture. And finally, the control system that we are using are quite basic because we are mainly using on-off control strategies that don't allow us to optimize the culture conditions. These overall characteristics also allow us to identify the major challenge to be solved for further development of this type of technologies, especially to focus in the optimization of the biological system. Also, we need to optimize the knowledge and the technology for modern engineering system, and especially we need to invest more efforts in the development of advanced control system that allow us a more robust and stable operation of this type of facilities. Then these are the major challenges that we must face. I repeat again, all of them are necessary if we want to develop more robust and larger production system capable to produce not 100 tons per hectare and per year. Sorry, not facility producing only 100 tons, producing 1,000 tons per year for real large-scale application of microalgae biomass. Then, concerning the biological system, entering more in detail about the topic, most of the people know that microalgae growth is determined by a series of factors influencing the performance of the microalgae cells. When we are talking about autotrophic production, of course, light is the main one, is the most important, but also the use of the light is a function of how we are able to control the temperature, the nutrient concentration, the pH, or dissolved oxygen that the cells are which the cells are exposed into the cultures. We already know that these phenomena are affecting the overall performance of the microalgae cells. We already know, or we already developed models able to predict the behavior of these parameters in the performance of the cells. Most of these models are obtained in the laboratory. I mean, we provide fixed conditions to the microalgae cells, and we are able to evaluate the response of the photosynthetic rate the photosynthetic response to the irradiance, to the temperature, to the pH, to the dissolved oxygen. We have plenty of models about these effects. However, in the real scale, the microalgae culture are not subject to fixed conditions. Then we know that outdoor, the environmental conditions modify daily and also along the seasons. That means that the cells are exposed to different cultural conditions. In the case of temperature, which is one of the most relevant, the variation of temperature of the culture can be in the range of 5 to 10, including 15 degrees, depending on the location and the scale of the reactor. And that means that the algae are subject to these different temperatures in the range of 15 to 40 degrees in one single day. And also, the timing that the cells are exposed to this temperature influence the performance of the algae. That means that we need to develop a more robust knowledge capable to simulate the photosynthesis rate as a function of this dynamic behavior. I mean, the light, not the light regimen, but the temperature regimen at which the cells are exposed to. Concerning the culture, it's very important also to focus in the microbiological aspect. I mean, the contamination of the algae by other algae, by predators, by viruses, fungi, etc. I want to remark the activities being performed in Prodigio project and Paraqua COSAction, because these projects are focused in this topic, how we are able to understand this phenomena and how to prevent this phenomena to avoid the failure of the reactors. Concerning the engineering, in the last years, we developed large advances in the improvement of engineering of the reactor, especially the fluid dynamic. The current use of computer fluid dynamic allow us to simulate the behavior of whatever configuration of the reactor without installing, of course, the system, but with a high precision in terms of evaluating the biomass concentration, not the biomass, sorry, the energy consumption, the pressure drop, the presence of dead zones, whatever problem that we can observe in the reactors. This is the reason because currently the size of the reactor is much larger than in the past. Only to remember that the regular size of one Raceway reactor is about 5,000 square meters, but today we are able to install single reactor of up to 1 hectare in total size. Also, we are working in the development of low-cost technologies, especially for low-value application of microalgae biomass as related with wastewater treatment, etc. Concerning engineering, also we must to fight with the problem of seasonal variation of sunlight and temperature. That means that we need to understand how the temperature and light available in the culture modify along the year and daily as a function of the culture condition we are providing. Then to be able to modify these culture conditions, I mean, especially the water depth, or at which time we are harvesting the microalgae biomass in order to maximize the performance of the cultures. again, in the last years, different models has been proposed for the optimal simulation of temperature in Raceway reactor that allow us to determine strategies, direct or indirect strategies for the control of temperature in this reactor, which allow us to increase the productivity up to 10% without investing more energy in the reactors. For us, one of the most important parameters is the daily variation of dissolved oxygen. To remark that most of the people is focusing pH control to provide CO2, etc. But if we are not able to remove the oxygen that is produced by photosynthesis, it's very difficult that the algae can perform up to optimal conditions. Then efforts has been devoted to optimize the removal of oxygen in the reactors, then allowing to increase up to 50% the biomass productivity with respect to system not adequately controlling the dissolved oxygen. One important question for microalgae reactor is also harvesting and processing of the biomass. The most conventional technology is to use centrifugation, but we must to think that centrifugation is really costly and also consuming too much energy. Then we need to develop low-cost technologies integrating per concentration and further the watering of the microalgae biomass. We believe that the use of membranes can be really an opportunity for these type of technologies. Finally, entering in the topic of advanced control system, later we will talk about simulation. To remark that also we were able in the last year to develop more standard system for the monitoring and control of microalgae reactors. In the past, only on-off system, quite simple monitoring techniques has been applied. But in the last year, the new facilities already integrate knowledge from this field. That means that we are able to have a more reliable data acquisition and control of this type of systems. It's very important, and in the last year, the European Commission also enforced the activities related with data management. Then not only to collect the data, but to use adequately this data for modeling, for simulation, and for evaluation of large reactors. Then also new technology has been or are being applied now for this type of developments. One example of control system is showed in this slide, how in a system that we are not controlling the pH, the productivity is much less than when we are controlling the pH, but including depending on the control system or the control strategy, the biomass productivity can increase a lot, only optimizing this type of technologies. Then today, the simultaneous control of pH dissolved oxygen allow us to increase up to 20% the productivity of this system with respect to older strategies. Then only to finalize, only to say that these type of technologies are already now in the field, in the industrial sector. All this technology has been transferred to the companies, and one example is the R&D facility that we have here in Almería, on which we are developing this type of technologies, but also we develop or we demonstrate these technologies in collaboration with companies like Biorizon. These are some images of the industrial facility, 1.7 hectares already available in Almería, producing microalgae biomass for biostimulants applications. And also we are quite proud of the 4 facilities that Aqualia is already operating in Spain for wastewater treatment using this type of technologies. I mean, microalgae-based technology for wastewater treatment. Only to finalize, to show the picture about the real project. We will talk again about this project, but in my opinion, this is a very important project because this is the first time that we consider the distributed production of microalgae biomass in different facilities and how we can centralize the management of this biomass in a single biorefinery capable to produce valuable product for different applications. That's all from my side. Then I think that we can perform the overview of different projects working on this topic. José Luis, you will share the screen.
Thank you very much, Gabriel. If you want, you can already start to share. Now we'll go over 5 minutes to present, 5 minutes per project. We'll present the DigitAlgesation, ALGAENAUTS, and Realm. Unfortunately, Joaquin Pozo was unable to be present, but Professor Jose Guzman will present on his behalf. We'll start with the DigitAlgae. So, Gabriel, take the stage.
Yes, I want to introduce DigitAlgae, which is an ETN network. I mean, it's a group of students working in a topic, and the topic is the development of knowledge in terms of modeling and simulation of microalgae processes. Okay, please, next slide. Yes, this is the objective of this project, to join efforts in order to be able to understand the biological phenomena taking place in these microalgae reactors, as I explained before. We need to understand the phenomena and to modelize this phenomena in order to be able to develop adequate strategies for the right operation and control strategies in this type of system. We designed from the beginning two major challenges to improve the light utilization efficiency, but as I mentioned, to be able to optimize the use of the light, we need to optimize the control of the culture conditions, and also, of course, to enhance the sustainability of business in this topic. Please, next slide. These are the partners already participating in the project. I want to recognize the effort that all of them are involving in this project, well-recognized institutions and companies. And you can see also the picture of the students, all of them performing very nice in this project. And the major advantage is that, including they are working in different topics, different aspects of microalgae processes, they are collaborating and sharing information between them, then contributing to the right development of their careers. Next slide, please. Then the project is still alive, more or less 1.5 years left. And then you can follow the progress about this project following the social media, etc. Thank you. Okay, I will explain also the project, the ALGAENAUTS project, because Joaquin cannot provide the presentation. The ALGAENAUTS project is a special project. You know that the European Commission have research project, but also project supporting companies. Then this is a project only provided to Biohorizon Biotech in order to be able to develop eco-friendly and sustainable biopesticide and biostimulant based on algae. This is a grant that they receive in competition with a lot of companies in Europe, especially SMA companies, and they were quite successful in the development of this project. Next slide. Yes, the project is supported with by the European Commission with approximately 900,000 euros, but the total budget is 1.4 million euros. That means that the company invest more or less 400,000 euros to develop this type of new products based on algae. I want to mention that Biohorizon is one pioneer company on the field of biostimulant from algae. Then they already have large experience on this field. They are already in the market. They are quite successful in the market. They are selling this type of products in around the world, not only in Spain or Europe. And the challenge for them is to be more sustainable and to increase the portfolio of products that they already have. Then, next slide, please. Then the idea is to be able to produce the agricultural products, both biostimulants and biopesticides, using microalgae biomass, but this biomass must be produced on a sustainable way. That means that we need to use residuals as a nutrient source, also to try to use flue gases or whatever, but to be able to produce selected strains using this type of effluents, we must to redesign the technologies to be used, especially control system and water management, because it is very important to prevent or to minimize the presence of contamination in these cultures, and also the sustainability in terms of using renewable energies for the energy supply. Please, next slide. This is the scheme of the project. Similar to the real project, it is planned to produce the microalgae biomass on the site where the effluents are produced, in this case manure. To manage manure is a little bit tricky because manure is very complicated effluent, but at the same time has certain advantage because it's a very rich in nutrients effluent, and we can manage this effluent very nice. The second part is the most important, is the biorefinery, because to be sustainable, we need to harvest the biomass from the reactor using membranes, but also to fractionate the biomass in the different products, biostimulants and biopesticides. We need to use sustainable technologies, mainly membranes, different types of membrane technologies, to be able to minimize both the energy consumption and also the release of waste from the process. That means that using the scheme already proposed, we are able to use 100% of the biomass to produce biopesticides or biostimulants. This is the challenge, and now we are in a right way to be able to accomplish this challenge. Yes, next slide. The project is mainly divided in the three classical topics: optimization of large-scale production of microalgae biomass. I repeat again, sustainable reactors and reusing waste as nutrient source, a scale up of the utilization of the microalgae biomass, always thinking about no waste and full use of the biomass for final products, and validation of these products in the market. They already have experience in biostimulants, biofertilizer, but now they are also gaining experience in biopesticides. Next slide. And also you can contact the company, Joaquin Pozo, or follow the advances in the project through the social media, and that's all from my side. Thank you.
Thank you, Gabriel. And thank you, Jose. So I'm Mariana. I'm Innovation Manager at Necton, which is the coordinator of the Realm project that I will explain briefly in this next few minutes. You can pass on, Jose, please. So as we already saw, microalgae are versatile organisms, and with this in mind, we also need to take into account that future policies will promote more sustainable production of several resources, and that the demand for algae-based products is expected to increase, especially in the EU. And introducing algae in the pipeline of different processes, such as horticulture, can bring several benefits. Although microalgae are exponentially growing feedstock for many applications, they are still limited to high-cost applications due to their production costs. So the Realm project, which stands for Reusing Effluents from Agriculture to Unlock the Potential of Microalgae, aims to make use of these obstacles by converting them into opportunities, by using microalgae to help treat drainage wastewater from agriculture into value. Next slide, please. So the goal here is to validate the integration of microalgae production sites next to soilless cultivation greenhouses and grow the algae in this drainage water. So basically have a decentralized production facility using 3 key inputs of water and nutrients, and used advanced modeling and deep learning tools to optimize productivity and nutrient uptake, resulting in biomass and nutrient-free water. Afterward, membranes in situ will concentrate the biomass, and this concentrated slurry will be transported to a centralized processing facility, where a biorefinery approach will be implemented to maximize the rentability of the biomass and develop products for both agriculture and aquaculture. In this way, we expect to support the development of innovative, competitive, and sustainable agricultural production with better management of natural resources such as water, and also promote the development of algae-based greener aquatic industrial processes and products, which is in line with the Green Deal objectives. Thank you very much. If you have any questions, feel free to send us an email, and also check out our website in the Realm website here below, Realm Algae. And next we'll follow with now with Jose and for the online simulation tool. Hope you enjoy.
Okay, thank you very much, Mariana. Thank you everyone for joining us today. So, as you could see from the Gabriel presentations, the production of microalgae in raceway reactors is a really complex process. For that reason, here we wanted to present a tool to contribute in the understanding of this complex system. The tool I will present later on is the one you can see here briefly. It's a tool where you can just simulate all the phenomena happening in the reactor. In the past, we tried to develop such a kind of tools to contribute in this understanding of the system. But at the end, it was a little bit complicated because you needed some kind of coding knowledge, or you need to install the application in a specific platform or whatever. But as you will see in a while, this tool is totally free and is independent of the platform, language, or whatever. It can be just run in a single web site, web browser. Okay, so. If we consider all the aspects mentioned before by Gabriel, where we should take into account the engineering phenomena, biological phenomena, and so on, the first step we need to do before developing a tool is to understand the process and to get a realistic model capturing all the phenomena happening inside of the reactor. So for that, we have developed a very big model representing all these characteristics of the process, and it has been divided in two different parts. A first part, which is called engineering model, which try to represent what happened according to the reactor configuration we have. And then this model has as inputs the weather conditions and the different manipulated inputs we can just modify in the system, like the air injection, CO2 injection, or harvesting and dilution rate. As a result of this part, at the end, what we have is the evolution in time of the most important variables happenings in the different parts of the reactors: the light availability, temperature, depth of the medium, pH, dissolved oxygen, and so on. And we can see how the effect of these variables is connected with the biological model, which is the other part mentioned previously by Gabriel. But that, of course, depends on the microalgae strain. Depending on the microalgae strains, the impact of these variables will be different. But it's not only that. The biomass concentration, because of this biological growth, is affecting also to the engineering model. So everything is connected. And this is something that we should learn before starting the development of a tool like the one I am going to present in a while. So, but it's even more complex because we realize what is happening inside of the reactor. We have also the gas and liquid phenomena and phases. And because of that, if we take a look to the models, at the end, we have so many equations which are related to each other and with more than 60 configurable parameters. So imagine how complex it is to understand a process like this. And this was our motivation. We need to develop a tool to contribute in the understanding of this system, not only for teaching and research purposes, but also for companies to evaluate and compare different production scenarios. So for that reason, the first step we did was just to work in the abstraction. I mean, how we can abstract all those phenomena and to understand the system like a box. So once we set a specific configuration of the reactor, and we want to analyze a specific microalgae strain, let's see what happens according to different weather conditions and according to different inputs into the system. And then we can analyze the outputs of the system according to those specific parameters and configuration. But not only that, this can be done to understand the behavior of the system in manual mode, to understand the different phenomena. But we can go even further just to see if we can improve the performance of the system analyzing different automatic control strategies. As Gabriel mentioned before, this is a challenge nowadays, not only to improve the performance on the system, but also to reduce the running costs of the facilities. And this is also something we wanted to include in the tool, not just the classical tool, including a model to understand the different phenomena happening inside, but also to compare different realistic scenarios, considering different weather conditions, manual mode or automatic mode with different configurations. So this is like the general scheme of what we can do with the tool. I will show you now. So at the end, how we have created the tool. We have the real system, and we were able to develop a first principle model. Once we got the model, we were working to develop just a easy visual representation of the system with all the parameters available to be configurable. When we had that, what we did was to develop the connection between the graphical part and the model. And now we are able just to simulate not only the behavior of the system in such a way that we can see what is happening like in a virtual reactor, but also which is interactive. And we can just modify the different parameters and to see the effect in real time this new configuration in the process. So this combination is what at the end we got like a virtual raceway or the online simulator we have developed. So as I told you before, the important issue of this simulator with respect to others developed in the literature is that it can be run in any operating system. It's also run in any device, mobile phone, tablet, or a computer. And the only thing you need is a web browser. We recommend the use of Chrome, but it can be run in any other web browser. And down there, you have the link where you can just access the virtual lab online, or you can download it in your computer or your tablet or the smartphone. So the good point of the simulator, when we have a simulator, we can make questions that are very difficult to evaluate in the real system, because we need to wait to the specific conditions to analyze the effect. We can compare different reactor configurations. We can compare different strains. We can evaluate what happened in different geographical locations, and you will see now. We can also analyze the different phenomena according to different options for harvesting and dilution rates, or the automatic control or not of dissolved oxygen and pH. So it's just like a simulator which is able to play with it. So what I'm going to do now is just to open the simulator and to show you the different parts we can find on it, and try to simulate different scenarios. So as you can see here, the simulator is divided like in two main zones. We can say that the graphical area is that one up here, and the parameters area, that one down here. So in the graphical area, we have like a visualization of the simulator. It's the classical visualization we can find in a real facility with an SCADA system and the main variables which are shown around. We have the solar radiation. I will explain you now that we are just including here a clear day solar radiation model in such a way that if you include the latitude and longitude of any place around the world, we can simulate what's happening if we place the reactor in that location. And also the main variables that we usually measure in the reactor, the oxygen, pH, the different flow rates, also an estimate of the biomass concentration, productivity, and some information about costs, running costs, in this case regarding CO2 gas injection. So on the other hand, we have a schematic view of the system to see the different valves and tanks which are part of the reactors, and to see how they can be modified along the simulation. And on the other hand, we have the view, the different main variables, the output variables. I'm going to run it while I explain the information. That way you can see what is happening. So we have here as I said before, the synoptic of the system, the output of the system, the inputs, and a general view of all the main variables, okay? As you can see here, now in these few seconds, we have simulated one single day. You can see how fast is the simulator. So this is the graphical part, as I mentioned you before. Down here, we can configure all the possible parameters. You don't need to modify all of them, but they're available in case you want to. because the simulator is also available for research purposes, okay? So here you can modify the dimension of the reactor. We can say the reactor configuration, the size of the reactor, the liquid speed, the sum dimensions, and the different harvesting and dilution rates. We can initialize the main variable of the system. We can evaluate different microalgae strains. You remember the Gabriel presentation, he presented the biological model that typically is calculated in the lab. And from those evaluations, we get all these parameters. In this case, by default, we have here the Cenedesmus almeriensis strain, but you can evaluate any other just taking the parameters from the literature. On the other hand, we have the global radiation model. You will see now that this is the location of the Almeria facility. So I will start making a simulation with this location, and then I will change it to another in Sweden to compare what's happening. We move the reactor from here to Sweden. And on the other hand, we can simulate just one single day, and we can set what is called infinite simulation. So the day is repeated one day after another. You can just simulate 1 week or whatever. And finally, we have the control part. And the control part, you can have the classical on-off controllers, as Gabriel mentioned before, or you can just set the manual control. It is no control at all. It's something that many people is still saying in literature. We will see just one single day what is the effect of having or not having control on the productivity on the system. And also you can just determine the harvesting and the dilution rates in manual mode or in automatic mode. So after summarizing the main ideas and parts of the simulator, I forgot to mention you that here you can just, you have the classical option, play, pause, and reset the simulation. And also you can record, you can collect the data as you are collecting data from the sensors. I mean, you start the simulation, you collect data, and you store the data in a file that you can open in any other software like Excel, MATLAB, or whatever for analysis purposes. So let's just run the simulation by default. Here, you can accelerate the simulation to make it faster. Here you can see we are simulating 1 day. Here you can see the power radiation, the depth. Here we made the harvesting and the dilution rate. Here we can see how the depth was modified because of that. The biomass concentration along the day, pH and dissolved oxygen, and the air flow and CO2 flow. Okay, so this is by default we have a PID control or the pH control and off control in the dissolved oxygen. As a summary of this simulation, here we can see the productivity. This was done for a day in Almeria in December, I think, in January the 15th, okay? And as a result, here you can see the productivity. It's a high productivity because at the end we are working in optimal conditions in the simulation. And this is the consumption we get relating the grams of CO2 injection with respect to the grams of biomass concentration we got, okay? So let me now compare these results with another for the same location without control at all, okay? So I will repeat the simulation. I will go now here to the control option, and I will switch off the control. No control for the dissolved oxygen, no control for the pH variable. And then I will run again the simulation. If we took a look to the variables, you will see now that there's no control of the pH of dissolved oxygen, and we can get very high value in both cases. And because of that, I forgot to mention you before, in the previous simulation, we got something like almost 27 grains per square meter per day. And in this case, without control, it's reduced up to 21. So you can see just in one single day, the impact of having or not having control of two auxiliary variables as the pH and dissolved oxygen. So another interesting comparison can be done modifying the location, as I told you before. In Almeria, remember, for this same day, we got about 26 grams per day per square meter. So I'm going to change the location and write here the location of Malmö in Sweden, okay? And I will run the same simulation, only placing the reactor in another location. And you will see the impact in the productivity. Remember 26 in Almeria, the same reactor, the same strain, the same configuration. 8.8. Only just by placing the reactor in another configuration. So you can compare also that, you know, how placing the reactor in another location around the world. Another interesting analysis is the following. In this simulator, we have the average temperature in the reactor. I mean, the temperature model is not included in the simulator, but we can set the average temperature. So by default here, we have 30 degrees in Almeria. This is the temperature of the reactor. And remember, we got 26 grams as productivity. I'm going to analyze now from 30 to 25, only 5 degrees less than before. And you will see the impact of the temperature, as Gabriel also mentioned before in his presentation. If we evaluate again the result, we can see how the productivity is decreased from 26 to 24. Okay, only remember, one single day, 5 degrees, the same period of the year. So, and then finally, another example I can show you is regarding the consumption, according to the having a good automatic control algorithm or a classical one as a on-off controller. So I'm going to run again the value by default to show you, you know, this is the good quality control of the pH according to a PID controller, which is defined here in these parameters. And this is the consumption. You see that we get something like a little bit less than 6 liters per minute. I'm going to repeat now the simulation just by using an on-off controller and setting the maximum value of liter per minute we have in the facility. And here, if we repeat with this new configuration, the simulation, first you can see the bad control we get here in comparison with the other one. Here you can see how high are the injections of the CO2 in comparison with the other. Remember, we were a little bit less than 6 liters per minute. But if we go to the first screen, maybe if we compare the productivity, we can say it's more or less the same, a little bit less, but the consumption is 20% more, only one single day. And not only that, the group of Gabriel Acien demonstrated that this variation in the pH can be critical for the microalgae growth rate. So it's much more convenient to have a stable value of the pH around of the optimal value which is set in the lab. And the same for the dissolved oxygen. Finally, what I would like also to show you is that every time you simulate a scenario, you can start the recording, and when you finish the simulation, you stop the recording, and you can get a file like this. You know, it's the classical file that you get in a real facility with all the variables that were already recorded, and then you can upload these variables to be used for analysis purposes in another different tool like Microsoft Excel or or MATLAB or whatever. So I mean, these are only a few of the examples we can run on the simulator, because as you can imagine, it's like a toy. I mean, we can still playing with the simulator and to make any question we want in our mind. We have in our mind. So okay, so this is everything for my side. So yes, now I think that the floor is open to all of you for any question you have.
Thank you.
Thank you very much for your attention. I will just share this screen.
Yes, thank you. We already have some questions in the Q&A. The first one actually is for Gabriel. Thanks Gabriel for the fruitful presentation about control strategies. Are there any updates on the use of AI for their implementation? As to the use of waste, what are the main legislative limitations on the use of algae biomass? What do you think we should avoid to focus on?
Concerning the use of effluents for the production of microalgae biomass, we must to consider that it is not allowed to use the final biomass for human applications, but you can use the biomass for whatever other applications. I mean, feed or agriculture, of course, materials or biofuels or whatever. There is no limitations in terms of regulation for using whatever residuals for the production of microalgae biomass, other that the convention, the standard regulation in the different countries about the management of effluents. I mean, to manage manure, you must to be authorized by your country to manage manure. It's the same that for wastewater. No, whatever person can manage wastewater. You must to be authorized to use this urban wastewater.
Thank you, Gabriel. And another question also to you. Did you find any challenges in collaborating with private companies for large-scale production for microalgae?
No, we collaborate with a large number of companies, including Necton, Biordizon, and a lot of them, and not except the restrictions in terms of information from one company to other, but that's all. But this is quite a standard for the academia, not only for Almeria.
I believe I can add that these days we are also growing in collaborating between universities, I mean academia and companies. So I think it's quite useful. Let me go ahead to the second one now to Professor Jose. Interesting presentation. Will the simulator can have a real-time replication accuracy versus the actual open PBR? So I imagine go ahead.
Yeah, the model was already validated using real data. But of course, you want just to replicate the real behavior of another different reactor. This is a model that is being used for simulation purposes, but you want to have a more realistic result. You need to take the model and to calibrate it with the real system, and of course, validate the results again. But and at the end, the good point of the simulator is just to get an idea of what is happening with respect to different scenarios. But if you want to use the model for design purposes of control purposes, of course, you need to calibrate it and validate it using real data from the real facility.
And another question: do we need to choose the algae strain in this platform?
Yes. Yeah, actually, by default, we're using Ceneresmus almeriensis, but the parameters is open. I mean, you can configure that option for the biological model with any other strain. Sometimes it's complicated to know the parameters, but nowadays you can find very nice papers summarizing the main parameters of the most important strains. So the only thing you need to do is just take those parameters from the literature and to put it there, or some other strain you are working on.
Okay, and the next one, in the virtual reactor, is it possible to change the Raceway reactor to another type, maybe tubular reactor or similar?
No, in this version. This version is just prepared only for Raceway reactor. Actually, in the past, in previous projects, we developed a similar model for tubular reactors, and we also developed a virtual lab for it. But at the end, as Raceway reactor as the most common one in industry, we focus the development of the virtual simulator on that model.
Thank you, Jose. The second question is actually quite similar, but I think what I can add to that question is, can we modify the Raceway, make it narrower, make it longer?
Yeah. Okay. It's open. The first parameter options, you can configure just the size of the reactor, the channel, the sump, also the paddle wheel speed. Everything is configurable from there. This is another interesting scenario. So that but I didn't have time to show all the capabilities of the two, but this is also possible.
We also have again another question. Is it possible to add more light sources to this virtual model? In example, both sunlight and LED light underneath the Raceway pond, for example.
Yeah, I mean, it's not included in this version, but this is a very interesting improvement to consider different light sources. And at the end, as the model is already available, the only thing we need to change or to supply to the tool is a new model, for the artificial light source. Yeah, but it's a very nice option to be included.
Okay. And they were wondering if at a smaller scale, does your system implement PEM measurements, so chlorophyll A fluorescence? In this case,
what did you say? Sorry?
Let me read it again. Thanks for the talk. I was wondering, maybe at a smaller scale, does your system implement PEM measurement? Chlorophyll fluorescence.
The PEM?
Yes. Yeah.
No, no, it's not included.
Yeah.
No.
Another one. The results from the platform are based on previous research or any algorithm?
Both. At the end, it comes from previous research where we develop the initial version of the models. And other algorithms we also develop in parallel. Because at the end, the tool is not just including only the model, but also the control algorithms. So all of them came for some of the contributions that were mentioned in the Gabriel presentation. There you can see some of the references where you can find the original equation of the model and some of the control algorithms we developed. The idea here was just to combine all of them together and to create the simulator with that information.
And in the case, if you don't have a sensor, for example, dissolved oxygen or pH, how will that parameter be taken care in the simulator?
I mean, with the equations, actually, we don't have any sensor in the simulator. The simulator is not using any real data at all. Everything is simulated. In some other simulators, people supply the real data as inputs to simulate the behavior, but it's not the case here. The only thing you need to set is the initial conditions, which is the initial value of the dissolved oxygen, pH, biomass concentration, and so on. And all the information is simulated from those initial values, as we are using also the radiation model as a light source. And the temperature is set in average, because just to simulate the temperature evolution around the world is a little bit more complex.
Thank you, Jose. The question from Lydia, well, we already went through it, virtual tubular reactors. So as Jose explained before, from another project, he already has, they already developed a model for tubular reactors. Jose, perhaps you can also tell where people can get this simulator for the tubular, for example, where they can access it.
Yeah, they can contact me, because we had it in another in an old project, but I think that the website is not available anymore. But people has my contact from the webinar information. Just contact me, and I can just send you a link with the simulator. Not only the simulator, but also the publication where they can get the equations for the model.
Thank you, Jose. Melanie, you want to add something?
I added another question in one of the comments as a comment to a question, so I think it went missing. So I just read it out. It says, any extra construction in the customized reactor will be taken care by the model?
No. The model only consider the standard flow in Raceway Reactors, then standard liquid velocity, etc. Then we didn't include the influence of the presence of buffers or whatever other questions in the turbulence in the reactor, because I understand that the question is related with the turbulence, the light regimen, etc. No, at this stage, the model don't consider this type of phenomena. But probably in further editions, we will include this phenomenon.
Yes, I believe this is already a quite helpful tool. Of course, it has to have limits. This is the first version, let's say. It's already quite advanced, and it can help a lot of researchers since we don't always have access to outdoor raceway reactors, for example, and we can mimic the conditions of an algae that we know outdoors. And in that sense, I think it is very promising. I don't know if we have any more questions. Let me check out the chat as well. How much does it cost to produce a kilo of biomass on a large scale raceway?
Mariana, you can respond this question.
Well, that can be hard. Sorry, Dario. You have to talk without commercial.
Yes, it's quite difficult to respond to this question because it will always depend on the biomass quality, also the resources that you are using, etc. In general, the idea is not possible to reduce the production cost below 5 euros per kilo. More or less from 5 to 25 euros per kilo is more or less the regular production cost, but it will depend also of the strain. If you are producing an hematococcus, the value is totally different. Then it's quite tricky to respond this question.
Yes, indeed. Okay. Let's see if you want to raise your hand, I can also give you the mic if you prefer to ask yourself.
And of course, as the tool is for free, I mean, any feedback after using the tool is very welcome. So, because as Mariana said, this is the first version, we are pretty sure that we can continue improving it.
And I think we are all very excited to start to test it out. At least I know we are.
Good, very good.
Okay, if there aren't any more questions, you have the contact. Oh, we have one. I know. We have the contact in the agenda webinar. You can also check out the Realm webpage, as I mentioned before. I hope you enjoyed. You'll receive a small questionnaire about how do you think the webinar went and what would you like to see next. So we can check out what are the main topics you would like to hear about. So thank you all for coming and joining us. I hope it was fruitful for your afternoon. And thank you for the presenters as well for taking their time and giving us a chance to learn something new. Thank you all.
Bye.
Bye-bye.
Thank you very much. Thank you very much.
Bye.